So good day, ma'am. We are here to present to you population dynamics under the topic in lesson 3, application of first order differential equations. So tulad po na nasa topic na nasa title natin ngayon, we have population dynamics. Ito po ang napili ng aming grupo na i-discuss. Application of first order differential equation. Differential equations were widely used to model natural phenomenon, engineering system, and many other situations. So tulad nga po ng sinabi dito, ang differential equation po ay ginagamit as a model. And when we say model is used to construct an approximate representation of the physical situation. The model is useful to predict the outcomes of experiments based on the physical situation. And because of this, the model is used instead of an actual experiment. So, differential equation is important in terms of application in real life situation. Na-apply po natin ang differential equation and it serves as our model. So, ano pa nga po ba ang kahalagahan ng differential equation? So, this enabled the engineers to avoid costs of experimentation, labor, equipment, and etc. Instead of doing trial and error, makikita na po natin mape-predict na po natin ang possible outcome sa isang certain experiment or project through differential equation. So, yan. So, under the application of first order differential equation, and we have mathematical model. So, marami po tayong mathematical model. And nga po, nakalagay po dyan, we have population dynamics, radioactive decay, Newton's law of cooling and warming, spread of diseases, chemical reactions, mixtures, draining a tank, series circuits, falling bodies under resistance, suspended cable, and etc. So, yun nga po, ang topic po na aming napili ay population dynamics. So, when we refer to dynamical systems, in fact, we are generally referring to an abstracted mathematical model, as opposed to the actual empirical phenomenon whose dynamics we are attempting to describe. We begin by attempting to identify the physical variables that we believe are responsible for the behavior of the phenomenon in question. And then, we may formulate an equation or system of equation which also reflect the interrelation of our assumed variable. And in this case, ang pinag-uusapan po natin dito ngayon ay ang population dynamics. So, ano nga po ba ang population dynamics? What is population dynamics? Population dynamics studies the changes in size and composition of population through time as well as the biotic and abiotic factor influencing those changes. So, in this study po, makikita po natin ang relationship between population and time. Na bibigyan natin siya ng equation mamaya po, na matatalakay po natin mamaya. Yan. For the past few centuries, ordinary differential equation, ODS, have served well as model of both single species and multi-species population dynamics. So, matagal na pong na-introduce ang population dynamics. The past centuries, ginagamit na po ito ng mga tao in different species. So, originally, population dynamics was introduced by Thomas Robert Malthus. Nga po, he introduced the Malthusian theory of population. And ano nga po ba ang theory of population na yan? Theory of population is a theory of exponential population growth and arithmetic food supply growth. Thomas Robert Malthus, an English cleric and scholar, published this theory in his 1798 writings, an essay on the principle of population. Let's have this background check kay Thomas Robert Malthus. During his time, 1798, that time ay Age of Enlightenment, and he observed na ang growth ng population ay patuloy na tumataas samantalang ang food supply ay kakaunti. And that's why naisip niya ang theory sa population na interrelated sa food supply. So, ang Malthusian theory na ito, itong theory of population, hindi lang siya applicable sa mga tao, kundi applicable din siya sa mga hayop. And an example pa nga ni Malthus doon sa kanyang gawa ay mga insect. So, yun nga, na matatalakay din natin mamaya sa ating general formula. So, ito nga, modeling population. So, we have dP over dt is equal to kt. So, dP is the rate of change of our population with respect to time. So, tulad nga na sinabi ko kanina, dito ma-explain natin ang relationship between population and time na in-introduce din ni Malthus sa kanyang theory. And nga po, where P is equal to population and T is equal to time, unit depends because it depends on the given species. For example, humans, usually ang humans, ang time natin dyan is year. While insect, alam naman natin na ang insect, mabilis silang mag-multiply. So, siguro, ang ginagamit po na unit doon ay day sa time ng insect. So, ang K naman natin dito ay constant. So, we have this general solution. To obtain this general solution, we have dP over dt is equal to kp. So, using this, i-apply natin dito ang variable separable. So, we have dP over dt is equal to kp. Multiply both sides by dt over p. Yan, cancel dt, cancel yung p. And then, napaghiwalay na po natin siya, na-separate na po natin ang variable niya. Pwede na po tayong mag-integrate. So, integrating dP over p is equal to ln e is equal to kt plus c. So, ayan nga po. To obtain the formula na p, kakanselin natin itong ln using this logarithm formula e, ln cancel. So, we have p is equal to ce raised to k e. So, ayun nga po, using variable separable, we can obtain the general solution of population dynamics. So, ngayon naman po, let's proceed to our sample problems na i-discuss po ng iba kong kagrupo.
Okay, let us now move on to the sample problem. First, problem number 1. The population of a small town grows proportion to its current population. The initial population is 5,000 and grows 4% per year. This can be modeled by the differential equation dP over dt equals 0.04 and P of 0 equals 5,000. First, letter A, we would have to find the equation to model the population. Then second, letter B, determine the population after 3 years. And third, C, determine how long will it take for the population to double. So, to find the equation to model the population, we're gonna solve this differential equation. So, if we rewrite this in differential form, we would have dP equals 0.04 p dt. Multiplying both sides by 1 over p, so we have 1 over p dP equals 0.04 dt. And let e raised to c equals p sub 0. Now we can integrate both sides of the equation and get e ln p equals e raised to the power of 0.04 t plus the constant integration. Moving on, p of t equals e raised to the power of 0.04 t e raised to c times t. P of t equals p raised to 0.04 t. Next, p of 0 equals p e raised to 0 equals 5,000. P is now equal to 5,000. P P of t equals 5,000 e raised to the power of 0.04 t. Now, after we get all of that, we can determine now the population after 3 years. First, we have to substitute the values. P of 3 equals 5,000 e raised to the power of 0.043. This will result to the number of 5,637 peoples after 3 years. Then second, how long will it take for the population to double? P of t as time equals 5,000 e raised to the power of 0.04 t. Now, we will get 1,000 equals 10,000 equals 5,000 e raised to the power of 0.04 times 3. Now we will have to divide both sides by 5,000. Then we will get the value of it later. Then we will go to ln 2 equals ln e 0.04 t. Ln e is equals to 1. Remember that. Open bracket, ln 2 equals 0.04 t, close bracket. Divide by 0.04. Now we will get the value of time equals 17.3 years. Alright, let us move on to problem number 2. The population of insects in a region will grow at a rate that is proportional to their current population. In the absence of any outside factors, the population will triple in 2-week time. On a given day, there is a net migration into the area of 15 insects and 16 are being eaten by a local bird population. 7 will die of natural causes. If there are initially 100 insects in the area, will the population survive? If not, when do they die out? Birth rate will be represented by the symbol RP. Okay, let's go on to the problem and then the solution. P prime of RP plus 15 minus 16 plus 17. P of 0 equals 100. P prime equals RP minus 18. Okay, P prime equals RP. P of 0 equals 100. P of 14 equals 300. The formula will be used is P of t equals C e raised to the power of RT. Applying the initial condition gives the population 100 equals 100. Now apply the second condition. 300 equals P of 14 equal 100 e raised to 14 r 3 times 300 equals 100 e raised to the power of 14 r. We need to solve this for the following. First, divide both sides by 100, then take the natural log of both sides. Then it will lead us to 3 equals e raised to the power of 14r, 100 e raised to the power of 14r. Then the natural log. Ln 3 equals ln e raised to 14r. Ln 3 equals 14r. Then finally r equals ln 3 over 14. P prime minus ln 3 over 14p equals negative 8p of 0 equals 100. Open and close parenthesis t equals e raised to the power of integral negative ln 3 over 14 dt e raised to the integral of ln 3 over 14 dt. Integral of p e raised to the integral of negative ln 3 over 14 dt equals integral of negative 8 raised to the integral of negative ln 3 over 14 d of t. P raised to the integral of negative ln 3 over 14t equals negative 8 times ln 3 over 14 e raised to the integral of negative ln 3 over 14t plus the c symbol. P of t equals 112 over ln 3 plus multiplied by 100 minus 112 over ln 3 close parenthesis e raised to negative ln 3 over 14t equals 112 over ln 3 minus 1.94679 e raised to the power of ln 3 over 14t. 0 equals 112 over ln 3 minus 1.94679 e ln 3 over 14t. Then time is equal to 15.44155 days.
So next example, problem number 3. A culture of bacteria grows proportion to its current population. If the initial population of 500 bacteria increases by 15% in 8 hours, what will the population be in 1 day? So from the previous example, dP over dt is equals to Kp. The general solution will be P of t is equals to P sub 0 times E raised to Kt. So the given will be P sub 0 is equals to 500, then P of P is equals to 500 times 1.15. 1 is initial value of 500, then 0.15 the bacteria increases. Multiply 500 times 1.15 will be 575. So be careful because K is not equal to 15%. So 1 day is equals to 24 hours. So substitute P of t is equals to P sub 0 times E raised to Kt. So substitute 575 is equals to 500 times E raised to 8K. So multiply both sides by 500. So it will be 1, then E raised to 8K. Then by using of logarithmic property, it will be ln 575 divided 500 is equal to ln E raised to 8K. So it will be 1. Then ln times 1.15 is equals to 8K. So cancel 8. Then it will be K. So multiply ln times 1.15 divide 8. So it will be 0.01747 is equals to K. Now we can substitute the general solution. P of t is equals to 500 times E raised to Kt. So the P of t will be P of 24, then equal to 500E times raised to 0.01747 times 24, which is 24 hours. Then it will be P of 24 is equals to 760.43, or P of 24 is equals to 760 bacteria. So in 24 hours, it will be 760 bacteria.